In today's lesson, we are going to be looking at rational exponents. So this is going to be a continuation of our power laws, or the review of power laws, but we're going to be adding a new concept to it, which is rational exponents, or in other words, fraction exponents. So just as an introduction to rational or fraction exponents, we have here a radical. And this is something that we've dealt with before. It just means a square root. Now there's a couple components or terms that we might not know of, but the number that's under the square root, this is called a radicand. And this value is raised to an exponent, or it's raised to an exponent right now. We don't see anything, but we can assume that there's a power of 1. There's also a value that sometimes goes here. Now, if we don't see anything in this spot here, similar to how we assumed that the exponent was 1, even though we didn't see it, if we don't see a value here, we can assume that it's 2. And this number is called the index. And this just basically tells us what root we're taking. Right? In this case, we're taking the square root or the second root. We're essentially finding two values that when you multiply it by itself, gives you x. You could find something, you could find the cubed root or the fourth root or the fifth root and so on. And all of this works out to x to the power of 1 over 2. So when we're dealing with radicals, we're essentially dealing with rational exponents, or vice versa. When we're dealing with rational exponents, we're essentially dealing with radicals. Now, radicals are only the square root. We're going to look at examples that have other roots. So it's similar, but not quite the same. So powers with a rational exponent in the form of 1 over n. So this is basically just saying where we have a fraction of 1 over 2 or 1 over 3, 1 over 4, where the numerator is always 1. So a power involving a rational exponent with numerator 1 and a denominator n can be interpreted as nth root of the base. So what that essentially means is, long and short of it is, if I have b raised to the power of 1 over n, this is equivalent to the nth root of the base. So this index is going to be our nth root. Let me actually just make this a little bit bigger. Just we have b to the power of 1 over n is going to equal the nth root. So the denominator becomes our index, becomes what root we're looking for. So let's go through and evaluate each of the following. So 8 and 1/3. So 8 and 1/3, this is the same thing as saying the cubed root of 8. So what to the power, or what times itself 3 times is equal to 8. And in this case, it is 2. On your calculator, you should have a button that sometimes looks like this, or it might be something like this. Right, so those are the buttons that are on your calculator that you can use to help you find the nth root other than the square root. So let me just redraw those. So actually on my calculator, I can see an actual cubed root one. So that's specific to cubed root. We should have a square root, one which actually means 2. And then you should also have one. On mine, it looks something like this. There may be other versions. Basically, it's letting you put in different values for that root. So the fifth root of negative 32. Now, if you don't have one of those buttons that we just kind of mentioned to do the fifth root, that's okay, because we can convert this to an exponent. And you should have at least an exponent button on your calculator. So the base is 32, the exponent becomes 1 over 5. So you could use your calculator, or you could say, okay, well, what times itself 5 times gives me negative 32? And in this case, our answer is negative 2. C, again, we're just evaluating, right? So if I wanted to, I could convert this. It's the fourth root of negative 16. So what times itself 4 times is negative 16. And actually, I just made a mistake when I was talking about it. Think about what is the base attached to, or what is the exponent attached to? It's just attached to this 16. So that means the negative stays out front, and we're looking for the fourth root of 16. Which makes sense because I can't do the fourth root of negative 16, because that means a number times itself 4 times would equal a negative number, and that won't work, right? Because it's an even exponent, so to speak. I wouldn't end up with a negative. But in this case, the brackets aren't included, so the negative is outside. The fourth root of 16 is 2, so this becomes negative 2. For D, similar things when we're dealing with exponents. So everything here is to the fourth root. So this is the same thing as saying 16 over 81, all to the power of 1 over 4. Or I could do the fourth root of each one, and I should end up with 2 over 3. So 2 times itself 4 times gives me 16. 3 times itself 4 times gives me 81. And lastly, negative 27 to the power of negative 1/3. So again, I want to convert it to a positive exponent. So it's negative 27, or it's 1 over negative 27 to the power of 1/3. If I want to convert this into a radical or into a root form, it'd be 1 over the cubed root of negative 27. The negative is included in the base this time because of that, the brackets. And the cubed root of negative 27 is negative 3. So this becomes 1 over negative 3, or negative 1/3. So this was just all about just evaluating the different powers with rational exponents, just making sure that we're comfortable either converting them or using our calculator to get those answers. Now, obviously, in some cases, we're not, or in certain cases, we're not going to always have the numerator be 1. So if that's the case, then we can evaluate a power involving a rational exponent with a numerator m and denominator n by taking the nth root of the base raised to an exponent, or the exponent m. So what that means is it's b. So for example, I'm going to convert back. So if I have b to the power of m over n we know becomes the root, b is the base, and it's raised to the m power. This is also equivalent to the nth root of b to the power of m. So m could be on the outside or it could be underneath. It would end up being the same thing. Now, usually we want to kind of stick with this format here, or that is more what we might see. So again, similar to the last one, except now we have a numerator that is not 1. Right, so let's simplify each of the following powers. So either we're going to write them as powers, we're just going to simplify them. So for A, the fifth root of y squared. So the 5 becomes the denominator. The 2 becomes the numerator. So this is the same thing as saying y to the power of 2 over 5. For B, the cubed root of x. Remember, x has a power of 1. If we don't see an exponent, we assume it's 1. So this becomes x to the power of 1/3. The power becomes the numerator. The index, or the root, becomes the numerator, or the denominator, sorry. C, this one is a little bit more challenging because now we're going to have to incorporate our power laws. So everything here is raised to the power of a root. We don't see anything, so we can assume it's a square root. So this is the same thing as saying a to the power of negative 3, b to the power of 4 over 3, all raised to the power of 1/2. I can use my exponent rules to simplify, so I can multiply all the exponents by 1/2. So a to the power of negative 3 over 2 times b to the power of 4 over 6, or you could say 2/3. a to the power of negative 3 over 2, b to the power of 2/3. I want positive exponents, so I'm going to bring the a power down. So I have b to the power of 2 over 3 divided by a to the power of 3 over 2. And I can't simplify that any further because they have different bases, so I'm going to leave it as is. D, similar concept. Everything is, so it's the fourth root of x to the power of 3y squared. So this would be the same thing as saying x to the power of 3 y squared all to the power of 1 over 4. Using my power laws, I can now multiply these exponents. So x to the power of 3 over 4, y to the power of 2 over 4, or this just becomes x to the power of 3 over 4, y to the power of 1/2. And I can't simplify that any further. They're different bases, so I'm going to leave it as is. E, kind of a combination, right? So I have the multiplication on the top, and I have division. So I'm going to simplify the top first. I do have to kind of convert this radical or this root or this rational expression. So it's going to be x squared y all raised to the power of 1/3 times y squared. That 1/3 is only applying to the values that are underneath the root or underneath the radical sign, the radicand, so to speak. So the x squared y is what's raised to the power of 1/3. I can simplify that. It becomes x to the power of 2/3 times y to the power of 1/3 times y squared, all divided by, oops, I missed that one for the last line. Got the divided by x cubed, divided by x cubed. I can simplify the top by multiplying my y values. So x to the power of 2/3, right? Add my exponents. So y to the power of 2/3 plus 1, or 2 plus 1/3 is 2 1/3, or 7 over 3, divided by x to the power of 3. We are subtracting, right? Sorry, we're subtracting our x values. So 2/3 minus 3 and minus 3, or 9/3. So we get y to the power of 7 over 3 divided by, I'm just going to do it off to the side, 2/3 minus 3 is 9 over 3. So I get negative 7 over 3. So I get negative 7 over 3, or essentially on the bottom, there is, x to the power of 7/3. And that is my simplified expression. The negative, it's telling us it needs to go on the bottom. So again, we can use our power laws with fraction or rational exponents. And same thing again when we're evaluating. So just a few more examples going through kind of the same concepts, just so we kind of get familiar with it. So 8 to the power of 2/3 becomes the cubed root of 8 squared. So again, I can plug this into my calculator, or I could say, okay, well, 3 to the power of, the cubed root of 64. So what times what times what gives us 64? In this case, it is 4. For B, 81 to the power of 5 over 4. Again, we're just evaluating. If we want, we can convert it to the fourth root of 81 to the power of 5. Right? Or if we enter it into our calculator, we should get 243. So again, this is more just about being comfortable using our calculator. C, 49 over 81 to the power of negative 3 over 2. Positive, we want positive exponents, so I need to flip my base. So 81 over 94, or sorry, 81 over 49 to the power of 3 over 2. That power of 3 over 2 applies to both parts, and we should get 729 over 343. So again, this is just about getting comfortable entering this into our calculators, converting it, writing it in different ways if we need to. Nothing too fancy in terms of the actual calculation, because all we're being asked to do is evaluate. Lastly, we're just going to look at simplifying and expressing the answer using only positive exponents. So this is just going to be using our power rules, right? So nothing fancy. Just going to work through them. Just go through a couple and then leave two with you to work on or try on your own. So I'm going to simplify the top. I'm going to add. So I get x to the power of 4/3 over x to the power of 1/3. Dividing power says we subtract. So we get x to the power of 3/3, or just basically x to the power of 1. B, again, power to a power, so we multiply. So we have y to the power of 2/4, or 1/2, times y to the power of -2/3. Don't worry about converting the negative exponents until you've simplified everything. Right? Save the converting negative to positive until the very end when you have a single power. In the meantime, go through and do your rules as normal. So I'm going to add my exponents now. So 1/2 minus 2/3. 1/2 is the same thing as saying 3/3. Or sorry, it's 3/6 times, keep it consistent, times y over -4/6. So when I add 3 plus -4, I get y to the power of -1/6. We want it as a positive exponent, so it becomes 1 over y to the power of 1/6. Keep in mind when we flip it or flip the base, we don't flip the exponent. So the exponent stays 1/6, we just turn it into a positive exponent. C, we have a power to a power. So again, this power of 2 applies to both parts. So 5 to the power of 2 is 25. 1/2 times 2 is just x. And then this is multiplying 4x to the power of -1/2. We can multiply our numbers. So 25 times 4 is 100. X times x to the power of -1/2. 1 plus a negative, or 1 plus a -1/2 is same as 1 minus 1/2, which is 1/2. We'll put the 1 there just so we know where we got the 1/2 from. And that's our simplified expression. I'll do D, and then I'll challenge you to try E on your own. So D is a little bit more complex because we have all of the different components. We have some roots in there that we need to convert to use our power laws. So m to the power of -2 to the power of 3. So we multiply our powers, -6. M to the power of 4 to the power of 1/2, because we turn this root into 1/2. M on the bottom, and we have then p, q, -3, all the power to the power of 1/2, because again, the root. M to the power of -6, m to the power of 2. We're multiplying on the top there. On the bottom, we get m, p to the 1/2, q to the -3/2. On the top, we add, so -4 over m p 1/2 q -3/2. I can subtract my m, so I have m to the power of -5 over p 1/2 q -3/2. I can't simplify those any further. I can't cancel anything else out or use my power laws in any other way. So I'm just going to convert my negative exponents to positive. So q to the power of 3/2 is now on top. P to the power of 1/2 is still on the bottom, and it is now joined by m to the power of 5. So that is my simplified expression. For E, again, similar idea, bunch of different components. So I'm just going to work through, simplify the top as much as possible, simplify the bottom as much as possible, and then divide. So x squared to the power of -4, we multiply our powers. We have y to the power of 3 to the power of 1/5. On the bottom, we have y, and then x minus to the power of -2, y all to the power of 1/2. X -8, y 3/5, multiplying powers. On the bottom, we have y times x to the power of -1, because -2 times 1/2, and y to the power of 1/2. I can still simplify the y's on the bottom. I still have x to the power of -1. The y to the power of 1 times y to the power of 1/2 gives me y to the power of 3/2, or 3, or 1.5, or 1 and 1/2. Now I can subtract or divide, so I'm going to subtract my exponents for the x. So I have x to the power of -8 minus -1, or -8 plus 1, so -7, and 3/5 minus 3/2. That's the same thing as saying 15 over 10, or sorry, 6 over 10 minus 15 over 10, because 3 over 5 minus 3 over 2 becomes 6 over 10 minus 15 over 10, which equals -9 over 10. So y to the power of -9 over 10. And because I want positive exponents, I'm going to move this just up here, or maybe I'll just, this is just off to the side. Because I want positive exponents, I would have to flip everything, or everything would go underneath. So 1 over x to the power of 7, y to the power of 9/10. So that is my simplified expression. So with rational exponents, the same rules apply. Everything that we looked at in terms of power laws is the same. We might have to convert from more of the radical form with the roots to the rational expression with a fraction exponent. And then, unfortunately, we have to work with fractions when we're dealing with our exponents. So same power laws, adding, subtracting, multiplying, flipping to get a positive. Same kind of rules apply, just now we're looking at it with fractions.